So we're learning about exponential functions. We started this in the lesson a few days ago, or last week. But continuing with that, exponential functions, I didn't mention this, are in the form a, b to the x. Okay, x is the variable. Okay, b will be some number, and a, we see that here that you can multiply the function by something, but a and b are numbers. The main thing is exponential functions when our variable is in the exponent. All right, so to graph these, we're going to start in the same way we graph lines, or we graph anything by using a table and putting values in for x, and then seeing what y the output would be. So we put in some values, we'll put in -3. And now, if you remember when we put in negatives, okay, what happens to this? You have 2 to the -3 is the same. Remember, negative exponents go to the denominator. So this would be equivalent to 1 over 2 cubed, which would be 1/8. And we'll graph this. I'll give you some graph paper so you can graph a little bit more precise. For the homework, you can just sketch it. All right, so we go to -3 on the x value, and we go up to 1/8, so it's going to be down here, approximately there, we estimate it. All right, we go up, so we get -3, we get 1/8. We'll put in, I'm going to go a little higher, -1. When you put -1, 2 to the -1 would be 1/2. So we see it's going up ever so little each time. Put in 0. Put in 0. Anything to the 0 power, remember, is 1. So we'll graph that. We'll graph a few positive values. We'll put in +1. 2 to the first power, when you put it in for x, is equal to 2. So when you put in 1, you get 2. Put one more in. 2 to the third power is 8. So that would be up here. Okay, so when we graph this, you see that exponential functions, the graph looks like this. They have this curve that goes like this, and when we see it's increasing more and more. Now, we see that this value, if we were to put in some more negative values, okay, less negative values, we keep going to the left, we see that this will get closer and closer to 0, but never hit 0. We call this line that the function is approaching, we call that an asymptote. And an asymptote is the line that the graph approaches but never will get there. Okay, so this would be a horizontal asymptote because the line runs horizontal at, and then that value would be y equals 0 is where the horizontal asymptote. Okay, they're going to ask you about that. The line's approaching that y equals 0, but it'll never get to that. As we talked about domain and range, we know the domain will never be 0, and we know the domain will never be any negative numbers. It will never fall below that in exponential functions. All right, number 2. Okay, we're going to see a pattern to this when we graph these. Okay, the only thing that changes is this number, this base for exponential function. So the base is 3/2, so let's take a look at what that looks like. Now here's the 3 values that I want you to put in. Okay, put in -1, 0, and 1. If you put those values in, you'll be able to get a rough sketch of any exponential graph. I know the book does more, but you don't need to do all of those examples. So we make a table x and y, put that -1 in. So 3/2 to the -1 power would be the reciprocal. We just flip it, so this would be 2/3. Put in our 0, we should know anything to the 0 power is 1. So when we put that in, 3/2 to the 0 power is 1, and then we put in a +1, and of course that'll just give us 3/2. So we do a rough sketch of that. Okay, -1, 2/3, okay, almost to 1, and then 0, 1, and 1 3/2. If we continue to put more values in, okay, we would see that the graph or the curve looks very similar, just a little bit different. This number, this base, changed the curve a little bit, but the basic curve always starts with this curve like this, okay, and then how much it curves is going to depend on what number this is, what number the base is. Right now we see there's a pattern. Okay, 3/2 is a number that is greater than 1, and so is 2. And we see that all those graphs are going to look like this, with just a little bit of variation. Now when we have numbers that are less than 1, we're going to see that that's going to change how my graph looks. Okay, we're going to have basically two types of graphs that are going to look similar. Those that have bases larger than 1 and those that have bases less than 1. So we'll go ahead and do the same thing, put these values in. I'm going to choose the same values. Now -1, when the reciprocal would be 3/2. We put in 0, again we get 1. We put in 1, we get 2/3. And so now we see with this, okay, we'll go ahead and graph those points. And we see that anytime, and this is going to be true for all of those with bases that are less than 1, okay, our curve is going to go the other direction. Okay, so we're going to know that they need to look like one or the other. They're going to be, some are going to be more curved depending as we increase that base, and some are going to be less curved. All right, now number 3 has a couple different things. I only showed one part, but we call these parent functions because all these exponential functions look like each other. Okay, the children, or as we change that number, changes it, moves it, shifts it. We should know, just like a parabola, when we take 2 away from this, we're going to shift. We're going to see that the graph is just going to shift it down 2. If we were to subtract from 2 from the x, it would shift it to the right. And so when we graph these, we're going to see the very same thing. Am I blocking that video? I think we're okay. All right, let's switch sides. All right, so do the same thing for these, and we'll put the tables above it. X, Y values, we're going to put the values of -1, 0, and 1. I know I'm going pretty fast. Anytime you can slow it down just to see how I got this. But 3 to the -1 is 1/3. 3 to the 0 is 1. And 3 to the first is 3. Go ahead and graph those 3 points. Remember, those are going to be my input. I'm going to use those values each time to graph this, get a rough sketch. All right, so we see 3 to the -3 to the x should look like one of these two graphs. And it should curve up to there. And actually, if you want to, you could just draw that bottom part of the curve. It doesn't change at all. Because we don't have precise values, you can just graph those and just start off with this curve, because you know it's going to do that. It's always going to go through 0, 1, and this part is always going to curve down to the left. Okay, remember that's an asymptote. This value is going to keep getting closer and closer and closer to y equals 0, but it's never going to actually equal 0. All right, then the one other value we put in, when we put 1 in, we get 3. 1, 2, 3, so we graph that point, and that shows us how much that's going to curve, how steep it's going to go, or how narrow. So we see that. All right, now we're going to do the same thing for this, and I'll show you. All graphs act the same way when you take away some from the equation. Okay, if we brought this over, we would be adding 2 to y, which shifts it down 2. We'll see when we plug in values that occurs. Okay, so we put in -1. Okay, let's get 1/3 minus 2. Okay, 1/3 minus 2, which would be -1 and 2/3. So graph that. So approximately, that'd be about here. All right, we put in 0. Okay, now 0 is going to be 1 here. 1 minus 2 would be -1. So we get the point 0, -1. Okay, and we see here we put in 1. We get 3 minus 2, which is 1. So you have the coordinates 1, 1. And we look at this and we can tell, okay, the curve, if I did this precisely, the curve is the exact same shape. The only difference is this graph is shifted down to. We'd see if I added or subtracted from x, that we would get the graph to look the same, but just shift left to right, left or right. All right, last one I'm going to do, I think example number 4 is a graphing calculator. We'll see if we can do those when we get in class together. But last one is example 5. Okay, in this one, it's talking about compound interest. The main thing, and you'll see these on ACT questions, is know how to use it. It's a big, scary formula. You just got to know where to put the numbers into, and a lot of times they tell you. All right, here's the formula to calculate compound interest. It says where P is the initial deposit. Okay, so P is the initial deposit, or the deposit that you put into the bank or into wherever you're investing in. Okay, R is the annual interest rate. Okay, that's the rate of interest. Okay, it says n is the number of times per year that interest is compounded. All right, and it says for this, suppose, and t is the number of years. All right, so it says suppose $20,000 is deposited into a college savings account when a person is born. So there's the deposit, that's the P. So what we're going to do is we're going to put $20,000 in for P. Substitute that in there. All right, now we're actually going to have to do this twice because they're going to have us do two types of interest, compounded yearly, and I think the other one is quarterly. All right, then it says saving amount when a person is born. How much will be in the account on the person's 18th birthday? All right, so 18th birthday, that means 18 years has passed. So that's going to be what we put in for T. All right, it says if the account earns 9%, that's our rate as a decimal, that would be 0.09. So that's what we're going to put in for R. And they want us then, it says, to find it quarterly or find it daily. So if it's quarterly, you split a year up into quarters, that means you're going to, the interest is going to compound every 4 years. Yearly, it's going to compound every day, or it says daily, so it's going to compound 365 times. And they want us to compare the two different types. So R again was rate, I believe that was 9%, so as a decimal 0.09. And number of times. So quarterly, it'll be done 4 times. We use that for both ends. Time amount that it was in there, 18 years from birth to 18 years has passed. All right, and we'll do the same thing. $20,000 doesn't change, but they want to compare it to if this was done daily. So we put in, the rate doesn't change, still 9%, but the times it's done, instead of just 4 times throughout the year, it's going to be done 365 times throughout the year. Okay, again, N is going to be 365. The time is the same, 18 years. All right, now it's just calculated into your calculator. So we want to be careful that we use the order of operations in doing this. I'm going to let you do this, and hopefully you get the same thing. But we're looking here, we want to do parentheses and exponents first. So see this, we want to divide this, add this to 1, take 4 times 18 and raise this to that power, and then multiply it by the 20,000. Okay, we've got to simplify inside the parentheses first, then multiply the exponent, take it to that power, multiply it by 20,000. When we do that, we get that if it was compounded quarterly, that they would have $99,263.32. But if we compound it daily, do the same process, add inside the parentheses, okay, we'll divide this, add it to 1, multiply those, take it to that power, then multiply by 20,000. We see that, of course, if it's done daily, you're going to make more money. Okay, you get $101,041.63. All right, so that's your lesson on exponents.